Lecture 9 this is called risk adjusted control charts. Now, today I thought maybe it's good to talk some history. I like giving these examples. Sadly, I don't have many examples because this is the first time I'm teaching. But I like to present examples, and this is one of the examples that I thought will be really interesting to some of you. So let's try to make this more interactive, okay? The plot that you see here, let's just focus on the plot. The plot that you see here is showing the number of excess deaths that happened under the primary care of this Dr. Harold Shipman from the year 1977 to 1997. So number of excess deaths. What this means is this is equal to number of deaths under the care of Harold Shipman. I'll just say HS minus number of expected, or let's say number of deaths expected after a surgery. Right after a surgery, if there is a terminally ill patient, then there is some expectation that that patient may not survive, right? So number of excess deaths is nothing but it is equal to number of deaths under the care of this particular doctor minus number of deaths that were expected after surgery. This is number of excess deaths. Now let's return to this plot and let's just focus on the female cases, okay? Female cases are shown by this filled circles, right? Now, take a look at this for a moment and tell me if you notice something wrong with this plot. If something is going wrong here.
The number has increased a lot.
Right. And would you be able to specify at what time, during what year this happened?
I guess after 1991 or
Right.
93.
Yeah, but if you use as general control chart analogy here, the number of excess deaths crossed the control limits around 1985, right? Around this time, it crossed the control limits. So what this control limit is essentially saying is the number of excess deaths significantly increased after 1985, right? So this tells you that there is something wrong. Now, typically this kind of a control chart became extremely famous around 2000s, where they started to use this kind of a control chart monitoring technique to find out if a doctor or if a surgeon is suitable to continue practicing, right? If they find any anomaly, they would ask the doctors or the surgeons to take training again, to go back and retrain. But definitely, this tells something is wrong with this, with the number of patients that are dying under the primary care of Harold Shipman. In fact, in 1998, at this point, Harold Shipman was convicted of killing more than 200 patients, mostly women. Now, at that time, there was no control chart. People did not use control chart, especially in healthcare. They did not. So people like taxi drivers or mailman, they saw that something is going wrong. The patients, those who were visiting this doctor, Harold Shipman, they were pretty healthy before visiting the doctor, but after the surgery, these patients became extremely ill and weak and eventually died. So in 1998, I think in March of 1998, Harold Shipman was convicted of killing more than 200 patients. But in his defense, Harold Shipman said that the patients who were visiting him, they were terminally ill, meaning they had higher risk of dying after the surgery. And it's a possible cause, right? If all of the patients who were visiting this doctor, they had, let's say, some pre-existing conditions, diabetes or high blood pressure or any other kind of pre-existing condition, then they would have a higher probability of dying, right? In other words, mortality of the mortality rate for these patients were very high. So with this excuse, the police actually closed the investigation in April of 1998. They did not found enough evidence, and people thought that Shipman is not lying, he is correct. But eventually, later on, they found that the patients who died, they had significantly higher levels of diamorphine in their bloodstreams. So this was one evidence that they found in September of 1998. And they also found a bunch of other evidence that established that Harold Shipman was uh, actually involved in killing these many patients. This happened in 1998, okay, September of 1998. In 2003, there was a statistician by the name of David Spiegelhalter, and David Spiegelhalter conducted an analysis of the patients who died under the primary care of Harold Shipman. What what David Spiegelhalter assumed is he thought that, well, Harold Shipman may be true. He may not be lying. He may be correct that all of the patients that visited him, they definitely had some pre-existing conditions, right? They have a higher risk of dying. So in 2003, this statistician developed a model where he can adjust the risk. He can adjust the risk of patients and construct a control chart after risk adjustment. So when he developed this methodology and he plotted the control chart after risk adjustment, he noted that, let's again focus on the empty circles and empty triangles, okay? Let's not focus on the filled circles and filled triangles. They are for male. We'll focus on female only. Now, after plotting the risk adjusted mortality plot, he noted that up until 1996, the risk adjusted values were within the control limits, right? But at around 1996, the number of excess deaths exceeded the control limits. So after taking into so just to summarize, after taking into consideration that patients have pre-existing conditions, David plotted another control chart by adjusting the risk. And he noted that after 1996, the number of excess deaths still crossed the control limits. But Harold Shipman was not convicted until 1998. And after 1996 till 1998, there were 52 excess deaths. 52 patients were killed. 52 patients were killed after 1996. So if they would have used this kind of a control chart methodology in 1995 or 1996, they would have been at least able to suspect that something is going wrong, right? Even after adjusting for the risk. But they did not use these type of control charts because it was not common to use control charts at that time in healthcare. But just giving you an understanding here that by using control chart, they could have saved at least 52 patients, right, if not more. So after around 2003, people started incorporating these type of control charts. This type of a control chart is called risk adjusted control chart, and this is the topic of this lecture: risk adjusted control chart. And this has become really, really common in healthcare practice. They try to use this type of control chart to judge if a practitioner or a surgeon needs training or not, every 5 years or 6 years. So this is called risk adjusted control chart. And this is especially common in healthcare application. Think about it this way. If you're a doctor and if different patients, let's say patients with heart disease are visiting you, they will all have different chances of surviving, right? If let's say there is a young guy, let's say 40 years of age, visits you versus someone who is 70 years old, they would have different probability, different likelihood of surviving, right, after the surgery. So there's always a risk involved in healthcare applications, and it is extremely essential to adjust the risk of the data before constructing a control chart. You want to adjust the risk before constructing a control chart. And this is known as risk adjustment. Now, how do we do risk adjustment? That's what we will talk now. There are typically, the way typically this is done is we want to establish a model. We want to establish a model connecting the raw observations X to the response Y that needs adjustment. Now let's understand what we are trying to say here. The response Y, let's say this is the mortality rate. Okay. Mortality rate, the one that we just saw right now in the plots. Your raw observation X could be age, gender, blood pressure, obesity, and a plethora of other factors. All of these factors can actually influence your response Y, mortality rate, right? So we want to find out a model that can connect these raw observations or X with the response Y, which is the mortality rate. Because if mortality rate is in reality influenced by age, gender, blood pressure, obesity, then if they're dying, that's not because of the doctor. That's because these patients had a pre-existing condition, right? That's what it means to risk adjust. Now, to establish a model between a response Y and your observations X, these are also called factors. Some people call them as factors, some people call them as variables, some people call them as features, and a lot of other terms are used depending on who you're talking to. But typically, there are two types of models that exist. The first one is a regression model, which is typically used for continuous data, and a logistic regression model, which is used for attribute data or discrete data, right? And I thought this might be a good segue to what we are going to study after this lecture, which is the multivariate analysis. And I think we'll also have some time for principal component analysis. So if some of you who are not familiar with machine learning models, especially, this might be a good way to get a quick introduction as to what do we mean by machine learning models, or what do we mean by statistical models. Okay. All right. So today I think we'll only be able to cover the first topic, which is regression-based risk adjustment, because we'll first consider the continuous data. All right. Any questions so far?
So far, so good.
Yeah. Go ahead.
No, I said so far, so good.
Oh, okay. Yeah, this is really funny.
Why is that?
Yeah, I mean, I look up and I see no one, and then someone is speaking, so it's funny, right?
You feel like you're talking to yourself?
No, I try to have the videos here, but it doesn't help too much because all of your videos are turned off. So it's all right. I just assume that I'm talking to people. The class is all empty right now. I can actually see empty chairs in front of me, but that's okay. I hope this thing goes away soon. I really hope. Okay, so let's talk about regression based risk adjustment. Now, some of you might be familiar with regression from your previous exposure, but we'll quickly talk what do we mean by regression And then we will come and talk about regression-based risk adjustment. Okay. So what we do in regression is typically we consider a relationship between some input variables X and some response Y. Again, this response, you can take an example of mortality rate. This is not the only example. If you look into manufacturing, your response Y can be weight of a component, right? It could be hardness of a material. So the response can be a plethora of things. Input variables are what you know. So for a patient, what you know is age, you know the gender, you know the blood pressure, you know if the person has diabetes or not. So all of these become your input variables. In terms of manufacturing, this could be, let's say, humidity, temperature, pressure, all of these will become input variables, right? Now, if you want to find out an out of control observation in Y, so far we have only worked with Y, right? We have been able to construct Shewhart control chart, QSUM control chart, exponentially weighted control chart, all for Y. We only worked with Y so far, right? But if you ask the question, why does an out of control observation comes in Y? Then an out of control observation in Y may be caused by two things. Either the system can be a person, or it could be a machine. So an out of control observation in Y may be caused by the system, or it could be caused because there's an out of control X. What it means is, let's say you have a manufacturing process and you have set the input temperature, right? If you have set the input temperature, but suddenly because of some external factors, the temperature suddenly changed, right? Now this change will change your response, right? In this case, the out of control observation in Y would happen because there is an out of control X, right? So the out of control observation in Y may be caused either by the system or an out of control X or both, right? So let's hold on to this thought and let's study regression, and then we'll come back and see how we can address each of these points. Right. Now, regression is basically you want to develop a model to connect your Y and your X. You want to connect these two, right? Now, let's say at any given time, K is time, XK is our observation, and YK is our response, all right? A regression model is basically given as some constant beta naught plus beta 1, which is the coefficient for xk, plus some error term, which is epsilon k. To be very specific, we are talking about linear regression. So we are not talking about any regression, but we are talking about linear regression. Now, beta naught and beta 1, these are called regression coefficients, or these are also known as model parameters, right? And epsilon k is your error, and this is always normally distributed with mean 0 and variance sigma square. And we also assume that the error is independently and identically distributed. These are the two assumptions that we make here, that epsilon follows a normal distribution with mean 0 and variance sigma square, and the values of epsilon are independently and identically distributed. Okay. And k is time here. Let me write that down. K is time. Now, this is in this case, I'm just using one variable, right? I'm using X as one variable. You can also generalize regression models to as many variables as you want, right? So if you have multiple variables, you can write down yk equals to beta 0, which is a constant, plus beta 1 x1k plus beta 2 x2k plus up to beta p x pk plus epsilon k, right? You can extend it to as many variables as you have. Now, once you are able to establish the regression model, now instead of monitoring y, we will monitor z. Okay, we are not going to monitor y now. We are going to monitor z. What is z? Z is at any given time t, any given time k, zk is equal to yk, which is our observation, minus beta naught plus beta 1 xk, right? I'm just considering one variable right now. This is our model with one variable, and zk, and this is nothing but your epsilon k. Does it make sense? We can estimate beta naught, we can estimate beta 1, xk is already given to us. So we can find out this term inside the parenthesis, and we can subtract this from the original value, which is yk, and we can get the error term. So instead of monitoring the y values, we are going to monitor the residual from the regression model. Okay. Now, if there is no change, if there is no change in zk, zk would follow normal distribution with mean 0 and variance sigma square. This is what we assumed, right? It follows a normal distribution with mean 0 and variance sigma square. But if there is a change, if there is a change in zk, zk will deviate from this distribution. All right. So what we have done essentially here is we have the system. We have the input variable, we have the response. We use the input variables to construct a regression model, right? We construct a regression model, and whatever we get from this regression model, we subtract from y, right? And we get z, and this is what we monitor. I'd say it's a little abstract right now. I'm just writing down in terms of variables and constants, but we'll use an example to see how this works, right? But before we use an example, we still need to estimate the parameters beta 0 and beta 1, right? Only then we can calculate zk, because we have yk, we have xk, but we don't have beta 0 and beta 1. So let's see how we can estimate beta 0 and beta 1. Now, the standard approach for estimating the parameters is called least squares. Okay. Estimate beta 0, beta 1, blah, blah, blah. Our model was yk equals to beta 0 plus beta 1 xk plus epsilon k. This was our model, right? And let's assume that we have some data points available for k equals to 1, 2, up to m. So we have all of these data points available to us. So I can write down y1 equals to beta 0 plus beta 1 x1 plus epsilon k. I can write down y2 equals to beta 0 plus beta 1 x2 plus epsilon 2. We'll replace k here. So this is epsilon 1. And we can keep on writing this up to ym, which is equal to beta 0 plus beta 1 xm plus epsilon m. Now, if you observe, these are essentially a bunch of linear equations, right? Now, one way to solve linear equations is to use least squares. What we do in least squares is, let's first of all write this down in the form of the matrix notation, okay? For matrix notation, I can write this down as y1, y2 up to ym. This is my left-hand side. This is equal to 1, 1 up to 1, x1, x2 up to xm. This multiplied by our regression coefficients, which are beta 0 and beta 1. Okay, plus the final matrix is epsilon 1, epsilon 2 up to epsilon m. I basically converted this system of linear equations in the form of a matrix, right? In the form of different matrices. Now I can also write this as capital Y equals to capital X times beta plus epsilon. Now these are all matrices and vectors. So what I will do is I will just put an underscore here to denote that these are not scalars, but these are vectors. So beta under bar is nothing but beta 0 and beta 1. Okay, so this is your matrix notation. All right, give me 1 second here. Okay, so now you have regression in the form of a matrix y is equal to x times beta plus epsilon, right? Now for least squares, it says that minimize epsilon transpose epsilon, right? You want to find out the value of beta under bar that minimizes epsilon transpose times epsilon. What is epsilon transpose? This is nothing but y under bar minus x under bar beta under bar transpose multiplied by y under bar minus x under bar and beta under bar. So once you minimize this, you can actually just take the derivative. You can do this later on. Just take the derivative with respect to betas and then equate it to 0. Once you do that, you can find out the optimal values of beta. So once you minimize this expression, you will get beta hat is equal to, this is under bar because there are multiple values of beta. So this will be x transpose x under bar inverse x transpose y. So this is your solution for least squares, and this is the value of your beta, where beta hat bar is basically beta 0, beta 1 up to beta m, your parameters. Okay, this is called least squares, and you can use least squares to estimate the parameters of the linear regression model. All right, any questions on this one? Okay, so now once you have the parameter values, now you can compute z, right? Zk now will be equal to, let's go back and let's take a look at the formula for zk. Zk is equal to yk minus beta 0 plus beta 1 times xk, right? So let's write this down. This is equal to yk minus beta 0 hat plus beta 1 hat times xk, right? This gives you zk, and this is also given as epsilon hat. Make sense? So instead of monitoring or constructing a control chart for yk, Now I'm going to construct a control chart for ZK. All right. Now, once you obtain ZK, you can use any control chart you want. You can use Shewhart control chart, you can use QSUM control chart, you can use EWMA, you can use MA, whatever you want. Okay. In this example, let's consider Shewhart control chart. Now, if we consider a Shewhart control chart, and if n is equal to 1, do you remember what type of control chart we can construct? If n equals to 1, we construct individual chart, right? Individual measurement wait a second. Individual measurement control chart using moving range. Remember the MR chart that we did in the exam as well as in lecture 5. So I'll just write down the formulas here quickly for your reference. N equals to 1, so we can calculate MR bar as 1 by m minus 1 summation of MR I, individual moving ranges, I equals to 1 to m, and then MR I is equal to your ZI minus ZI minus 1, right? This was your moving range. And once you have this, you can write down Z bar, which is equal to 1 by m summation of ZI, and your UCL will be equal to Z bar plus Z alpha by 2. So we can just assume a 3 sigma control chart. So this will be 3 times MR bar divided by D2. And similarly, your LCL will be equal to Z bar minus 3 MR bar divided by D2. And remember, you find the value of D2 for n equals to 2, right? And your center line is equal to Z bar. So that's everything about regression that we want to use in this class. Okay, regression and regression-based control chart. Now, so what we have done so far is, instead of plotting a control chart for Y, now we want to construct a control chart for Z, right? Now, so we want to construct a control chart for Z. Let me go back to one of the slides that I introduced in the very beginning. Yeah, this slide right here. I told here that if there is an out of control point in the response Y, this may happen because of the system, or because there is an out of control X, or because both of them are, because there's something wrong with both of them. The system is basically your Z that we just calculated, right? Your X is already available to you, right? So now, instead of constructing a control chart for Y, we will construct 2 control charts. The first one will be for Z, which will represent your system, and the second will be for X, which will represent your inputs. Okay. So now let's go to this table. Now you have 2 control charts. You have an X chart and you have a Z chart. X chart is for inputs. This is for inputs, and this is for the system. Now, when X chart signal means out of control point. All right. So when there is an out of control point in X chart, and there's also an out of control point in the Z chart, that means both input and system are out of control, right? If only X chart signals, we mean that X is out of control. And when only Z chart signals, we say that the system is out of control. System is out of control, right? And the last is when there is no signal. If there's no signal, then everything is in control. All right. Okay, so let's consider an example here. Now, I made up this example because I could not find, again, a real example. But I will actually upload a paper that's very interesting paper. It's about cancer. And they will do a very similar kind of approach that we will talk right now. But it was very difficult to download the data. You have to go through some kind of NIH registration and blah, blah, blah. So I could not download the data, but I will share the paper on Canvas so you can take a look at that. And it's very similar to what we will see here. So consider the weight of cardboard manufactured during a day. Okay. When I say during a day, it's from time k equals to 1 to k equals to 40. This could be anything time, but we'll just consider 40 different timestamps throughout the day. The level of humidity affects the water content and eventually the weight of the cardboard. This is known. Okay. The variables measured are x equals to humidity. So x is equal to humidity, which is our input. And y is our weight of the cardboard or the response. Now it says plot and compare the conventional and the risk adjusted control chart for this. Right? So let's just use y, right? And use y and construct a regular individual measurement control chart that we have studied so far. So here I have timestamps from 1 to 40, which is your first column. Then the second column is the weight of the cardboard. And the third column is humidity, right? Now, if I want to construct a conventional control chart, I will forget about humidity right now. I will just focus on the weight. So if I use weight time 1 to 40, and I construct an individual control chart, you will notice that a lot of these points are outside control limits, right? These points and these points are outside the control limits. Now I want to find out why these points are going out of control limit. Is it because something is wrong with the system, the whole process that is manufacturing these cardboards? Or are these points getting out of control because there's something wrong with the humidity, right? Humidity is your X here. Weight is your Y here. Make sense? So we're asking the question, why are these data points outside the control limits? Is it because there's something wrong with the system, or is it because the humidity levels are wrong? There's something wrong with the humidity levels. So to do this, first we have to do regression. We will try to develop a model between Y and X. There's just one variable, right? So if there's just one variable, I can write down our linear regression model, Y equals to beta 0 plus beta 1 X plus epsilon, right? If you had two variables, you can write down Y equals to beta 0 plus beta 1 X plus beta 2. Let's say the third variable is, I don't know, W. So you can write down W. Okay. Now we can use least squares, and using least squares, we can estimate beta 0 hat and beta 1 hat, right? So I used least squares and I constructed and I did regression. And upon regression, I found that Y was equal to 9.6827 plus 0.1989 times X. This is our regression model. This is your beta 0 plus this is your beta 1. No need to write plus here. And you can see that it's a straight line that fits all of these observations. Y is your weight and X is your humidity, right? So now that we have y, let's call this y hat. This is y hat because we have used beta 0 hat and beta 1 hat. Now I can find out zk. This is nothing but yk minus yk hat, right? Yk is your weight, initial weight that is given to you, and yk hat is what you estimated by using beta 0 hat and beta 1 hat. Now, once you have zk, we again construct the control chart for zk, right? This is again the individual control chart. And when I construct an individual control chart, I notice that all of the points are inside the control limits, right? If all of the points are inside the control limits, this basically means that there's nothing wrong with the system. There is nothing wrong with the system, right? Because all the data points are inside the control limits. And remember, Z is your system, right? Now, the last thing is I also want to monitor the input X. Now, when I monitor the input X, I notice that there's something wrong with the input. The humidity levels are varying throughout the day, right? Before somewhere around T equals to K equals to 15, and somewhere after K equals to 24, my humidity levels are outside the control limits. So that means there's something wrong with the humidity. Something is wrong with humidity. This means that if you want to ensure the quality of the cardboards, you want to make sure that you control the humidity levels. Does it make sense? So this is how we have taken out the effect of humidity. And after taking out the effect of the humidity, we realize that there's nothing wrong with the system. There's actually something wrong with the inputs, X. Okay. So this is regression based risk adjustment.